Good afternoon, everybody. My name is Martina Naughton. I am a business development manager responsible for high performance computing in EMEA, so Europe, Middle East and Africa. So today what I'd like to talk to you about is some of the collaboration projects that we are driving. Predominantly, my main conversation is around the projects in Europe, so I'm not talking about anything outside of Europe. So essentially, the Open Power Foundation, which was established in 2013, as we saw at the very start of this presentation, the number of companies participating is growing and growing. And what we're finding is that one of the key core motivations for participating in the Open Power Foundation is that it is a catalyst for innovation. It is a forum whereby member companies can collaborate, drive innovation, and essentially translate those findings into new products, new research, and so on and so forth. Today, what I would like to talk to you about in detail is some very specific collaboration projects. So, in June 2015, the British government unveiled essentially a 5-year joint collaboration between IBM and the Science Technology Facilities Council. So, in short, that refers to STFC. This 5-year investment was actually an extension of their commitment to the Hartree Centre in Daresbury, and it was a commitment also for IBM to roll out a technology programme, but also to have researchers on site. So essentially, one of the fundamental points and one of the fundamental objectives of this research is that from IBM's point of view, we believe that there will be considerable technology transfer of advanced computing and big data analytics, and this will translate into new products, new services and new manufacturing processes. Furthermore, this will translate into new experiences for users. So users such as researchers, doctors, engineers, researchers will be able to make will be able to use big data to make decisions quicker and cheaper, and will be able to make new discoveries in a more effective manner. From STFC's point of view, they will actually be accessing open power high performance data center computing servers. We are in the second generation of those servers at this moment in time. But in addition to this, they will be leveraging technologies from the Open Power Foundation members such as IBM ourselves, NVIDIA and Mellanox. So there's multiple parties involved in this. So when we think about this programme, the fundamental objective from the British government's point of view is to establish the British industry and academia to be the forefront of research, and to actually translate this work into allowing British industry to have a competitive advantage. When we talk about competitive advantage, we talk about competitive advantage in an 18-month time frame. So they want to have industry get an 18-month head start on their competitors. And in order for the British government to be able to accelerate UK competitive advantage, it's absolutely essential, it's recognised that it's essential that they create a strong R&D centre. So as a part of this collaboration between IBM and the STFC, there are going to be 100 researchers, research staff and scientists on board. That will be broken down between 35 IBM research staff and 65 STFC research staff. As a part of this collaborative project, there's going to be significant hardware and infrastructure platforms rolled out. And at this moment in time, those infrastructures include open power clusters such as ESS, Flash, NVIDIA, Mellanox. From a software point of view, there is use of Watson cognitive cloud capabilities, big data analytics and big insights, amongst many others. In order for this programme, this collaboration to be successful, it's recognised that they have to build on existing UK strengths. And when they talk about building on existing UK strengths, there's a few facets to that. One facet is leveraging the existing capabilities within the Hartree Centre, which was in existence prior to this announcement. Leveraging the existing R&D collaboration and leveraging that R&D collaboration for economic impact. And also connecting in very closely with UK academia so that they can actually leverage the excellence in the various domains. So coming back to the idea of accelerating innovation in key technologies, so some of the core outputs of this programme is to establish the UK as a leader in cognitive computing technologies and to develop the next generation data-centric systems to enable cognitive and big data. This 5-year collaboration programme has a number of focus areas. So if we actually talk about the focus areas, there's 3 domain areas. One is life sciences with a particular focus on genomics, precision agriculture, food sustainability and security. Another focus domain area is science, engineering and manufacturing. And within that, there's specific focus on multi-physics components, machine learning component and fuel jet simulation. The third domain area that is a focus of this 5-year collaboration is within the domain of chemistry. And specifically within chemistry, we're talking about computer-aided formulation, machine learning component, and HPC in the cloud. These 3 components will feed into this sector, this section which we call enabling technology. And when we talk about enabling technology, we talk about enabling large-scale machine learning. We talk about algorithm implementations to exploit data center services. We talk about visualization and visual analytics and computational steering, and we talk about cloud. We talk about tools for HPC in the cloud. So in terms of the work to date, I'd like to give some examples of work at this moment in time that we're seeing already at the early stage in this collaboration. So typically HPC is focused on increased speeds. However, what we have found with one particular program of work is that when we actually use machine learning to make we can use machine learning to make better decisions on which simulations give the most value. So when you look at this chart here, each dot represents a simulation, and this is relevant to a computational chemistry problem. And what we found is applying cognitive machine learning and cognitive workflows together with HPC, we found that we were actually able to reduce the number of calculations by 1/3, which is very, very significant. And we're also able to increase the magnitude resolution by 4 times. So in terms of the work, when I spoke initially about this program, one of the core components of it to be successful is to actually translate, to use technology to address real industrial scientific problems. So with this in mind, it's absolutely essential that we have close collaboration with industry. So looking here at this slide, we're talking about some of the work that we're doing with Unilever. So all of the work that our researchers, both IBM and STFC, are doing, take the position that it all starts with the consumer. So some facts here about Unilever. I'm sure everybody in this room knows Unilever, less maybe as a company, but definitely as a consumer. So when we actually talk about Unilever as a consumer, if you just look at some of the figures, they are startling. There's over 2 billion consumers worldwide using Unilever product on any given day. They are selling the products in over 180 countries. They have been in the markets such as Brazil, China, Indonesia for over 50 years, and today their sales, 53% of their global sales are coming from the emerging markets. So when you think about that, this is a company that is dealing with some very, very considerable size of business and scale of business. So going back to what I said earlier on, we always start with the consumer or with the customer, and in this case our customer here is Unilever. So what we actually look at is we take the customer's wants and desires and we translate that into a technical target. In terms of, look at a consumer product such as Persil. What we would typically do is we would design new experiments, and the design of the new experiments would be to look at formulation. And within the formulation, what we would do is we would test the effectiveness of a number of ingredients within the formulation, and we would participate in criteria matching. And when we talk about criteria matching, we talk about things such as the ingredients compatibility, the structures of the ingredients, and how all of this will lead to a decision on whether or not it's an appropriate formulation. We then apply high performance computing. We apply computer analytics simply because it radically speeds up the process. It radically speeds up the time to which we can arrive at a decision. So what we are finding is that increasingly we are moving away on the left-hand side from what you would call a wet lab environment, so a traditional experiment environment where the PC is nothing more than a glorified typewriter, should we say, to a scenario where we are working with a IT deeply interconnected, enabled system, whereby on the first side, experiment is king. The experiment is king, but it's a different type of experiment. It is an experiment, for example, that focuses on high throughput. We also see that visualization, as an example, is becoming increasingly important. And visualization within that, the ability to distill between big data and small data is becoming very important. And being able to pull out the relevant information, we believe that that's going to contribute to the inventive step. We also see that in terms of the various ingredients within a formulation, this can be barcoded. And then another step on this is just to make the users of this, to make it easier and more accessible to the user. So in terms of that, what we talk about is a situation where we want to try and remove the researchers, the people in the companies that are responsible for formulation, and move them away from the real experiments to a situation where they can access their computer simulations on a handheld device, and they can do this with very, very little time investment. And what this means is it frees them up for more time, shall we consider it thinking time, more time for them to focus on product design, more time for them to focus on the establishment of new hypotheses. So another collaboration that I'd like to touch on throughout the day, there's been conversations and various points about Barcelona. So essentially IBM and BSc have a long history of collaboration in Barcelona. This chart gives you an indication of how far back the relationship goes. But if I take a point in time, and I actually take 2005, we entered into a collaboration in 2005, and that was a 6-year period of collaboration. It was an extended, an additional 2-year period onto the first point. So essentially, when we actually look at this collaboration agreement, the collaboration was around high performance technology, specifically high performance architecture, programming, application performance, a whole area of topics within high performance computing. Some of the core work streams that are involved in this is how do we design microprocessors? How do we develop programming models that allow for easier use for the users? What tools can we be developing to actually help with application performance? The collaboration continues, and there's some other areas that are of continued interest. Within new areas of interest are cognitive computing. So the idea of leveraging data-centric systems to develop the solution. Another area that's of particular interest is genomic sequencing and health simulation, and cognitive development through alliances with universities and institutions. This is also an area that, as I said, we have a long history of collaboration. So the idea, similar to STFC, leveraging the knowledge and capabilities of universities and institutions is absolutely key. So another example of collaboration that I'd like to briefly touch on is CDAC. This is a ministry in India. They're responsible for research in IT, electronics and manufacturing. So essentially the main aim of this collaboration is to support scientists and engineers to target challenges in the areas of energy and environment, healthcare and big data processing. There are very specific work streams within this collaboration, and you can see some of them yourself there, but some of the most interesting ones are the ability to evaluate programming models, and the ability to scale applications in science and engineering towards petascale range, and the ability to create competence and knowledge for HPC application developers. This point of the ability to create knowledge, that is a consistent theme that we're seeing in many collaborations. The idea that you can create knowledge, you can develop an ecosystem, you can participate in training and sharing knowledge and experience is very, very important. So in terms of this particular collaboration, CDAC's approach is to explore the best possible performance on the open power systems that they have available to them. They participate in a number of benchmarking and testing and porting and profiling the benchmarks, and the specific ones that they did were Stream, LinPack, OpenFOAM, GPU Bench and MPI. At this stage in the collaboration there's some preliminary findings, and in terms of the preliminary findings from CDAC, they have concluded at this point in time that open power ecosystem provides new opportunities for co-design and research. In actual fact, they joined the Open Power Foundation in 2015, and one of their reasons to join in 2015 was that they wanted to be able to access, similar to other collaborations, they wanted to be able to access an ecosystem of other members so that they'd have the opportunity to collaborate. Now that they've kicked off their collaboration, they have concluded that that this ecosystem does indeed provide new opportunities for co-design and research. They found as well that this ecosystem is absolutely essential to enable heterogeneous architectures required to meet challenges. At this point in time, their results that they see on the benchmarks that they have carried out, they describe them as positive, interesting and insightful. And the final point that there's a number of conclusions that they arrived with, but these are the most telling. The open power as an infrastructure meets a number of challenges of future petascale systems. This slide here, as maybe some of you, or maybe most of you know, we made a very recent announcement, and that recent announcement is our new, shall we call it, NVLink server box. We have called that Mscape. There's a lot of information. We have created our own blog, and I'm very happy to share that with you afterwards. However, the creation of this offering is as a result of a 4-year journey, collaboration journey with NVIDIA. What we're seeing at this point in time is that this server, essentially, which couples 2 power-rate CPUs with up to 4 Tesla GPUs, and is available as a 2U Linux server. What we're finding is, based on our current benchmarks and tests, is that we're seeing unprecedented performance and application gains. We're seeing, actually, if you look at the slide on the top right hand side, it gives you some very specific examples of performance benchmarks. So looking at Kinetica, which is it's a database that is used heavily in logistics, retail and financial services. We're finding a 2.5% performance improvement, Kinetica on Mscape, versus a competing server that's using PCIe. Similarly, with applications such as CPMD, we're seeing over a 2 times performance improvement. And for such an application which is used in computational chemistry, a performance improvement of that is very, very meaningful and very, very significant. The other point I will make is that Lattice QCD, we have seen a performance just under 2 times. Once again, because of the type of application, it is very meaningful. The core point about this slide here is that In terms of the Mscape, what is unique about the Mscape is it allows direct connection not only between GPU and GPU, but between CPU and GPU. So this is a solution that will address a problem, which is the ability to feed, the ability to unseat the bottleneck that has been created and that we've seen with the PCIe. So as a result of this, what we are expecting in the market is we're expecting an increasing amount of applications to be operating and to be running on GPU. So we already ourselves are beginning to see evidence of that with the amount of requests and requirements for applications on GPU. So the final point I'd like to make is this idea of collaboration with our partners is absolutely fundamental, and what we have over the past few years have been doing is actually creating almost a network, a hub across Europe of what we call Power Acceleration Design Centres. So the first Power Acceleration Design Centre, I think it was announced in November 2014. This is actually in Germany. This is a collaboration between ULIC, NVIDIA Europe and IBM research labs in Böblingen, Germany and Zurich. So the core mission statement behind this power, so shall we say the PAD, this Power Acceleration Design Centre, is to really support scientists and engineers to target grand challenges facing society. And those grand challenges, this particular PAD focuses on grand challenges within the area of engineering and environment, within the area of information, and within the area of healthcare. So within healthcare, you're talking about brain research, so there's quite a lot of work going on there, and there's genomics going on there. You've seen this trend before, but a core mission statement of the PAD in Germany is to create competence and knowledge for application developers and technology developers. There is a PAD in France as well that was established in 2015 in Montpellier, and that is a collaboration between NVIDIA, between Mellanox, and between the IBM Client Center in Montpellier and Zurich Research Labs. Mission statement there is to actually provide direct support to customers. So customers who have porting and tuning requirements, that centre is available to customers to come to and they can get help. To expand the software ecosystem around open power, and to increase computational performance and energy efficiency. And the final part of their mission statement is to advance the development of data-centric research, industrial and commercial applications. And the last PAD is actually STFC. So STFC, I think they actually announced it the end of 2015. There was a press release in 2015, and this is actually the PAD in STFC is a collaboration between IBM Research, STFC, Hartree Centre at the Daresbury Labs, and their mission statement is to create a test environment to essentially enable or to get industrial-ready applications in open power. Obviously, the mission of the PAD and STFC is compatible with the mission of the overall project, the overall collaboration, which I spoke about in detail earlier on. So to essentially drive economic impact in the UK by collaborating with academia and industry, by developing softwares and algorithms, and by expanding training and skills. That is me. Does anybody have any questions? No? Okay, very good. Thank you.